Super cool.
Just one thing. I did get an email. I'm sure everybody else got it too, but the president is having like a video cam kind of press conference thing where students can actually ask her questions directly. So if anybody had questions for her, then they can do that tomorrow at 2.
Yeah, awesome. Yeah, I mean, it's all a really fluid situation. We're trying to work with you guys as much as possible, but this has been a curveball for us as well. You know, all the summer stuff has been moved online. They're even telling us to prepare for the potential that the start of the fall semester is going to be online as well. So this has all been a bit weird. But again, y'all are making my life so much easier. I'm so happy to be teaching organic chemistry this semester instead of one of the lower level courses, because I have heard horror stories about herding cats. Okay. So anyway, so this chapter 18, we're going to start talking about benzene, right? The only thing that we really knew about benzene up until this point is from chapter 8. It's not a bad time to go and review some chapter 8 notes. If you guys, I'll actually go ahead and post those on Canvas if somebody can remind me if I forget. But that was really in chapter 8 was when we were talking about resonance structures as well as aromaticity. And that's really all we know about benzene up until this point, is that it's aromatic and has conjugated bonds, right? But we don't know any chemistry that really involves benzene, which is kind of wild because benzene is incredibly, incredibly important in terms of organic chemistry. It is prevalent in terms of biochemistry by quite a bit. As it's noted here, this is a pretty crazy fact, but 2/3 of drugs that are on the market right now contain a benzene ring. We know because we worked on in lab, right? And so many of the organic chemistry experiments that we've done, we've been using these compounds that have benzene rings in them. The one thing to remember about benzene, again, this keyword, aromatic. And remember that what it meant to be aromatic was that aromatic compounds just have that much more stability associated with them, right? Lower free energy. The free energy that you get for forming an aromatic compound is very, very low, right? That makes them very stable, okay? Yes. So first of all, one thing we're going to just have to get out of the way right now is the nomenclature for benzene. And we're going to sort of split this up into 2 different parts in this chapter. The first thing we're going to do is focus on just what are called monosubstituted benzenes, right? So a benzene ring, there's only one thing sticking off of it, okay? Yeah, so, and unfortunately, because of how, crucial benzene is, a lot of these simple benzene-containing compounds are referred to solely by their common names, i.e. the IUPAC system has incorporated these common names into them, okay? So actually, let's take a look down here real quick at what some of these are. These need to be memorized by that, it really means that there's no systematic way to come about them. In terms of what I expect you guys to know, we're going to simplify this list down a little bit. Certainly these 3 here. Toluene. Okay, so toluene is a benzene ring with a methyl group. Phenol, something we've actually already sort of come into contact with. Benzene ring with an alcohol group. And aniline is a benzene ring with an amine group. Okay, these are the 3, I think, most important. The other key ones here, although I feel like they're way more intuitive, are benzaldehyde and benzoic acid. All right, those are other just ones that I feel like, you need to be able to sight recognize. When we're talking about benzaldehyde, that needs to sort of click in your mind exactly what we're dealing with here. The other ones, whatever, we'll look those up, okay? But those 4 or 5, I guess, are pretty key here. So then in terms of like our systematic approach for how we get at these, again, just talking about these monosubstituted ones. So the first thing is, in the simplest case, the benzene ring is treated as the parent chain, right? So that's what's going to come at the end of all of these names. So it's bromobenzene, chlorobenzene, nitrobenzene. Remember nitro, this NO2 group, that's a nitro group. We're going to see something kind of special about these nitro groups later in this chapter. And then I think also important here are these alkyl benzenes, right? So notice that this is ethyl benzene because there's a 1,2 carbon alkyl chain on there. So then what would this guy be? Well, that's a cyclo.
Propylbenzene.
Propylbenzene, awesome. All right, and then what if we have a substituent off of that as well?
1, 2, 3, 4. Isobutylbenzene.
Yeah, totally. So you can go iso with it, right? But in terms of our common names, let's just note we would number 1, 2, 3. So this could also be 2-methyl-propylbenzene. Whoa. Okay, so that's what happens when you have a substituent on there. This only works when the benzene is at like a carbon 1. Okay, so we'll see what happens in a second when that's not the case. So when the benzene is part of the parent chain, the name ends in benzene. If it's off of the parent chain, if it's a substituent off of the parent chain, then you're going to have to refer to it as either a phenyl group, which is when it's just the benzene ring, or a benzyl group, which is when there's a carbon in the middle, or a carbon connecting it to the parent chain. So let me show you what I mean by this. So let's say we have a butane here, but now there's a substituent off of that chain. This would be 2-phenyl-butane. Okay. If you had said something like 1-methyl-propylbenzene, that's not exactly correct, but honestly, I would give you a good bit of partial credit for it. I hate the naming, I don't like nomenclature, period. I especially dislike the nomenclature when it comes to benzene, because I feel like there's not as systematic of approach of when it's the prefix phenyl or when it's the endpoint benzene. So I'm going to give you some leeway on that in terms of partial credit. But again, this one would be 2-phenyl-butane, because the benzene ring is not on what would be considered the parent chain. Okay, and then another just example of when you would have to refer to it with the benzyl prefix, that would be something like, so again, I have this long chain that's going to be my parent chain, but now I have a carbon in the middle. All right, so everybody take a second and see if you can't give me what this would be called. All right, so again, this is now an example of a benzyl group. Oh, this might have been a good example. Oh no, we're good. This is 3-benzyl hexane.
What if it has more than one CH2 in between the benzyl and the parent chain?
Yeah, so then it's going to be, you would consider it to be a benzene compound with an alkyl substituent.
Gotcha.
Yeah, so the only two choices are phenyl and benzyl. There's nothing after that. Okay. All right, so now let's get into the interesting part here, the actual reactions, okay? So first of all, electrophilic aromatic substitution reactions. That is this class of reactions that we're going to be learning about now. Okay, so first of all, here we got a benzene ring. That's of course going to be a key player in this chapter. And then here we have, this is going to be where I'm going to just demonstrate like this generic reaction mechanism. And we're going to see 5 different reactions that follow this generic scheme. Okay, but here Y is just my little variable that I'm using for the generic form. Notice that Y has a plus sign on it. So what is the, what does that mean? Y is?
That the benzene is the nucleophile?
That the exactly. So if it's a Y has the plus sign, that means that this guy right here is an electrophile. And then absolutely right. That means that benzene is going to be playing the role of the nucleophile in these reactions. Okay. And in particular, it's that double bond, one of those pi electrons in benzene that's going to be playing the role of the nucleophile. Similar to what we've seen for our alkenes, right? So here's my electrophile. It's like this guy here is what's going to be the nucleophile. Okay. And then these are going to be substitution reactions. So notice what's being substituted is the hydrogen that used to be attached to the benzene is going to be substituted out for whatever that electrophile was. All right, so we've seen a crap ton of nucleophilic substitution reactions. This is now an electrophilic, specifically aromatic substitution reaction. Okay, so anybody got a guess on what the first step's going to be?
Nucleophilic attack.
Nucleophile attacks an electrophile. Yup. Boom. All right, now everybody take a second and draw me what the intermediate is going to be after this step happens.
It's going to make a carbocation, right?
Yeah, absolutely. Yeah. So let's take a look at that carbocation real quick, make sure everybody has it. All right, so if we look at our original benzene here, that double bond is playing the role of the nucleophile, right? That means that one of these carbons, specifically this one I'm going to color in green here, has that pair of electrons snatched from it. Right, so that leaves it with a positive charge, i.e. the carbocation. The other carbon is still holding on to that pair of electrons and now forms that new bond with our electrophile. All right, so in terms of who's who here. So, right, so basically what I'm trying to make extra special sure nobody makes the mistake of is putting the carbocation, that positive charge, on the same carbon as that electrophile is attached to. Right, that's not what happens. It goes to that next door neighbor. And then we have a carbocation here. But of course, that's going to be stabilized by these various resonance structures that are available. Oops. All right, so because it's a benzene ring, that carbocation, that positive charge, can be stabilized. Okay, so then the last step, it's got to be a substitution reaction, right? So that means I need to get rid of that hydrogen that's currently on that same carbon. For this, we need any sort of a generic base, right? There's going to be some base in this reaction mixture that's going to reach and grab that proton, and that pair of electrons will come down and reform that double bond. All right, so it's a substitution. Really, you can think about it as an addition followed by an elimination. right? And again, just make sure you're keeping track of where that hydrogen's actually going to be removed from. It's going to be removed from the carbon that has formed that bond with the electrophile. Okay, one of the reasons I'm kind of trying to hit this, make a big point of this, is because when we draw benzene, we never draw the hydrogens that are decorating the outside, right? In this top picture, it's sort of written out here, but that's kind of rare. You never see it like that. So just keep in mind that this is indeed a substitution that's happening. Okay, and again, this is going to be
this whole reaction. It's a substitution, or just in a certain part?
Say it again.
Is this whole reaction is a substitution, or just a certain?
This whole reaction is a substitution. So if you want, so if we look at this top bar here, what we're substituting is one of our hydrogens that were on our benzene ring for our electrophile, right? Those are being swapped out. So at the end of the day, I have my electrophile attached to the benzene ring, but that's going to necessarily imply that one of those hydrogens gets pulled off as well. And so again, this is going to be this sort of like generic reaction scheme of electrophilic aromatic substitution, and we're going to see 5 different examples of this. Okay. First one are going to be with the halogens, so halogenation of a benzene ring. Okay. We're going to see what role the iron 3 bromide and the iron 3 chloride are playing. Let's hold off on that for a second. Everybody take a second and draw me what my product is going to be. You can pick any one of the two. They're closely related. All right, so again, I just want to make sure everybody's thinking substitution. And let's just note that benzene is not sort of reacting with these halogens in the same way that we would expect like an alkene to. So, right, what would happen if I had instead what would happen to my alkene?
It would turn into an alkane. It'd be reduced.
No, not with BR2.
Elimination reaction?
No.
Get a dibromination.
Dibromination, awesome, yeah. So in the case of reacting bromine with an alkene, you get the di-substituted product. Both of those bromine atoms will end up popping up. In this case, it's not the same. Okay, so let's go through and we'll look at the reaction mechanism to see why that is. But again, what we're going to see over and over and over again is that benzenes don't behave the same as alkenes. There's a reason why we put them in 2 separate chapters. There are double bonds, that pi electrons are acting as the nucleophile, but again, you want to have these in 2 separate categories in your mind. Oops. Okay, and the important part here is actually the role that that iron 3 bromide is playing. Okay, it actually has to activate this bromine in a way that makes it even better of an electrophile. Okay, we're not used to seeing bromine playing the role of an electrophile, right? What's that key property of electrophiles? Are they electron rich or electron poor?
Poor.
Electron poor, right? Bromine we do not think of as being electron poor at all. It's got multiple lone pairs of electrons surrounding it. It's relatively electronegative. So in order to make it a good electrophile, that's what the iron bromide is doing.
So it's bonded to it?
Yeah, so what we're going to see, whenever the metals are involved, there's something weird that's not quite a covalent bond called a coordination. It's going on, but nonetheless, yes, you can think about it as being bonded. It's now sharing those electrons with that iron 3 bromide. And in doing so, that makes that pair of electrons even easier to be donated, making that, right, we want to break this bond in this direction here. So that makes that terminal bromine, the one sticking out on the very end, an even better electrophile than it was before. Okay, and now from here, it's just our generic electrophilic substitution electrophilic aromatic substitution reaction that we saw before. You have the pair of electrons on the benzene ring acting as our nucleophile, attacking that good electrophilic bromine. That pair of electrons gets donated to that bromine with the positive charge. So this creates this, I don't really know what that guy's called. Iron tetrabromide ion, I don't really know. Okay, everybody take a second and draw me the other product I'm gonna get in this reaction, this step here. My other intermediate.
It'd be a benzene with a carbocation and the bromo attached to it, right?
Yeah, right. So, and again, I'm going to beat this like a dead horse here. I want to make sure that everybody's putting that carbocation, that positive charge on the carbon next door to where the electrophile is being added. Right? And then, in order to actually have a successful substitution reaction, I got to get rid of that hydrogen there. Right? So that's the next step in this reaction mechanism, is going to be this elimination, where we have just this generic base in our reaction mixture, attacking that hydrogen, and that pair of electrons comes down, reforming our aromatic benzene.
Could the iron tetrabromide be a base?
No, it's eventually actually going to kick off that extra bromine. So at the end of the day, you're actually going to be forming the HBr. Yeah, see, these are going to have generic base in the reaction mixture, our B with the lone pair. Okay, so again, notice that this bottom half here follows just exactly that generic scheme that we laid out on the previous slide, right? I guess it was 2 previous slides. The top part, the sort of activating of that bromine, I think that's going to be the hard part. In each of these 5 reactions, you're going to have this same sort of activation of your electrophile happen. And that's what's going to be different between the 5 reactions. What happens after that is going to be the exact same. Okay, but this activation step is what's going to be a little different between them. Yeah.
For this reaction, we're just using a generic base, not like any specific one, right?
Correct, and we're going to see that sort of over and over again in these next 4 reactions that we do.
Because it could be any base, literally.
Yeah.
Gotcha.
Just something there to accept that proton.
What would prevent, say, if you use hydroxide, how would you prevent that from attacking that cation intermediate?
To be honest, that's a good question. That's going to partially why we're going to just leave it as generic base at this point. The other reason why that isn't going to happen is because benzene really wants to form that aromatic ring again, right? It's not going to break its aromaticity for very long. It's not really happy to do so in the first place, right? So it's only really going to do so in such a way that, you know, it can swap out that hydrogen. That's why we don't have addition reactions with benzene, but substitution, because it's all about maintaining that aromatic benzene ring.
So with that in mind, would the bromobenzene be less stable than the normal benzene ring?
So that's a really good question, and something that we're going to sort of address in like halfway through this chapter here is what happens when we substitute these benzene rings. And I'll give you a little preview. It's going to have everything to do with whether or not your substituent is electron withdrawing or electron donating. This is something we talked a little bit about in chapter 8 as well. But let's pump the brakes on that. We'll sort of circle back around and compare multiple substituents on the benzene ring. Okay. It turns out with iodine, you're going to do, right, so that was with chlorine and bromine. With iodine, you can do things a little bit easier because iodine will actually form iodine cation. All right, everybody just take a second and think about how weird that is, because we're very used to seeing our halogens forming anions, things with negative charges. Iodine, in the presence of an oxidizing agent such as peroxide and acid, will actually form a positively charged iodine cation. Okay, yes, that is super bizarre. The only sort of explanation I have as to, why is that even possible? Things are very weird when the elements get really, really, really big. Okay, so iodine is enormous. Its ability to manage what's going on in its outermost shell is just that much more depleted because it's so much further from the proton, from its nucleus. All right, so it doesn't really have as tight of a grip on those outermost electrons as we would expect for our smaller elements. Again, so here the weird part is generating that electrophile. That's going to be the same sort of weird part in all of these reactions that we see. Here are electrophiles that positively charged iodine cation. So everybody take a second and give me the reaction mechanism that we're going to get starting from this point here. All right, I believe in y'all.
The benzene ring, can it have other substituents attached? Or no, wait, it wouldn't be a benzene ring then. Never mind.
No, so Cynthia, that's a really good question. Again, we're going to sort of explore what happens when there are different substituents on the benzene ring here in a second. We're going to find that some of them make them more reactive, some of them make them less reactive, et cetera, et cetera. So we're going to definitely get to that layer of complication. For now, let's just deal with the naked benzene ring.
Gotcha.
Okay. All right, so we have our nucleophile attacking our electrophile. This forms our carbocation intermediate here. Then we have generic base reaching over and grabbing that hydrogen, reforming that double bond.
When we do these, do we have to do those intermediates, the carbocation intermediates, or can we just go do like this shorthanded version?
Well, if I'm asking you for the reaction mechanism, you do, right? Because this second step here is crucial. Otherwise, you're not actually accounting for what happens to that hydrogen by just jumping from one to the other, right? So it's one thing if I ask you what the product is, that's simple enough. But if I'm asking you for the reaction mechanism, I'm specifically looking for this sequence of arrow pushing.
Understood.
Cool. And then Sam, I just, you had a really good question. Let me just stress something real quick. When we look at that carbocation intermediate, we're like somewhat trained to think electrophile, right? Carbocations are usually playing the role of an electrophile. So we see that intermediate and thinking, oh, a nucleophile is going to attack. Remember that carbocation intermediate is being stabilized through resonance. So that positive charge isn't localized on one carbon. It's sort of spread out throughout the entire ring. So it's not the same sort of electrophile carbocation that we're used to seeing. Yeah. I don't know if that's more or less helpful, but anywho. All right, so now moving on. So those are our halogenation reactions. These are going to be nitration reactions. So let's just look at this reaction scheme real quick. We have nitric acid, which is a super strong acid in and of itself. And we're going to get a substitution to create a nitro group on our benzene ring. But notice that we need an acid catalyst here, right? So even though nitric acid is a strong acid, we also need the presence of sulfuric acid. So these acidic conditions are going to be super crucial here. And again, the hard part, or the weird thing that's different than than all the other reactions, is going to be this sort of activation of that nitro group. Okay, so let's see, clearly it's that acid catalyst that's involved. Let's see exactly what happens here. And this is all about turning what was nitric acid into a really good electrophile, right? So that's the same sort of weird stuff we saw in our previous reactions as well. We had to first convert bromine and iodine to a good electrophile before it can actually react with benzene. So this is what's happening with nitric acid. We have oxygen that's going to act as a nucleophile and come over and grab that proton, that acidic proton, off of our sulfuric acid. Okay, that's going to create this type of intermediate here. And what do we know about this kind of group here?
It's a good leaving group.
It's a good leaving group. Awesome. So that's the next step, is this guy gets kicked off, and what we're left with is what's called a nitronium ion. This is our electrophile, right? So again, the first step, the hard part, is the actual preparation of that electrophile. First thing we got to do is form that nitronium ion.
This is one of the cooler nitrogen names I'd like to point out.
Yeah, it is pretty badass, yeah. The nitro group in general is just pretty cool sounding. Okay, and then I won't make you guys do it this time, but I'm going to make you do it again here. But let's just go through. From here, it's the same as in all of our electrophilic aromatic substitutions, right? Benzene acts as a nucleophile, comes and attacks this newly prepared electrophile. This creates our carbocation intermediate. We then have a base that comes along, grabs that hydrogen, and that pair of electrons gets donated back to that aromatic ring.
I have noticed that the base doesn't necessarily have a negative charge on it. Is that significant, or?
No, and really, your book is a little bit cryptic about it, but it has to do with this idea that in acidic conditions, you shouldn't have negative charges, right?
Oh, yeah, that makes sense.
Right, so they just want to have it so that when that base is protonated, it has a positive charge instead of hanging out there with a negative charge.
On the test, is it okay to use a generic base for the mechanism?
Yeah,
Okay.
Absolutely. Okay, so then the next one sulfonation. Okay. Here we have just sulfuric acid, as well as some heat is needed to catalyze this reaction. Sulfuric acid is, of course, a very strong base. That's not true at all. A very strong acid. And then the first step here is going to be the preparation of that electrophile, right? Or generation of the electrophile. So just like we saw before, everybody take a second and see if you can't figure out what happens. I'll give you a hint. It's sulfuric acid that's reacting with itself. And the scheme is incredibly similar to what we saw before with nitric acid. So see if you can't figure out how we prep our electrophile. I'll even give you what that electrophile looks like here so you know you're on the right track. All right, so we have going to protonate that OH group. This is going to form our good water leaving group that gets kicked off, and that's what forms our sulfonium ion. Okay, and again,
how does the sulfonium ion have a positive charge on it?
Because this pair of electrons gets taken from it and donated to that water. Does that make sense?
Yeah, well, I just tried to draw just like a Lewis structure of sulfonium, and
yeah, so if we want to look at, that's a good point. Let's just look at what exactly this looks like here. So you're going to see it SO3H, but let's just draw exactly what that's going to look like. All right, remember.
Oh, so the hydrogen's bonded to the oxygen, not directly to the sulfur.
Correct, absolutely, yep. Right, because remember, we're starting with sulfuric acid, which is this guy here.
Gotcha, yep, okay.
All right, and this is actually in equilibrium with SO3 and acid. All right, and so for this one, I am going to make you do it. So now, give me my reaction mechanism of the reaction between benzene and the sulfonium ion. All right, so per usual in these, we have the benzene ring acting as a nucleophile, attacking that sulfonium ion, our newly formed good electrophile. This forms this carbocation intermediate. We then have some generic base coming and removing up that hydrogen, and that pair of electrons now gets donated back, forming our benzene ring, aromatic ring. Okay. As opposed to the other reactions, this one's actually one that is readily reversible. Okay, so if I have this, my sulfonated benzene in the presence of acid and heat, I will get the reverse reaction occurring as well, where I will chop off that sulfonium group. Okay, so if we just want to look at the reaction mechanism here, again, benzene acting as the nucleophile. In this case, an acidic hydrogen is acting as the electrophile. We again form our carbocation intermediate, but since this is the reverse reaction, it's not the hydrogen that's going to be removed, it's that sulfonium group that's going to be acting as a leaving group. And then as we saw before, this compound here is in equilibrium with SO3 and H+. Okay, so it's really, you can remove that sulfonium group as well, acid and heat, right? So basically these are in equilibrium. There's not one, it doesn't strongly favor one side of this reaction or the other. One side of this chemical equation, I guess. All right, so the next ones I think are cooler. So the first is going to be the reaction that takes place between acyl chloride and benzene. What do we think is going to be the nucleophile?
Acyl? I'm just kidding.
Oh, Eric, you're hilarious. No, yeah, so of course it's the benzene ring, right? The benzene ring is going to be our nucleophile. What's going to be the electrophile?
The acyl chloride.
Specifically?
Carbon.
Oh, the carbonyl carbon.
The carbonate, right? Electrophilic carbonyl carbon. Hopefully I've drilled that into y'all's head at this point. But yes, so we got this guy, this carbonyl carbon that's going to be playing the role as the electrophile. However, notice that we still need some sort of a catalyst here. So again, we're still going to have this first step that's about generating that electrophile. The bottom line is that a benzene ring, we're going to see it acting as a nucleophile. It's not a good nucleophile. It's, again, it's quite stable. It doesn't want to break its aromaticity. So if you're going to have it behaving as a nucleophile in a reaction, you better give it one heck of an electrophile. Right? So that's why each of these have this first step of preparing a really good electrophile. But again, these are just substitution reactions. So in terms of the product, let's just see what we're going to get. Here is how we can get an acyl group. And then we could do the exact same thing with our acid anhydrides. Remember that these behave almost identically to the acyl chlorides. They're also going to get an acyl substitution. The only difference is that the other product is going to be, anybody remember what the leaving group is on an acid anhydride?
Is it a carboxylate?
Yeah, right. So it's this bond right here that's going to be broken. And so you end up forming a carboxylate or a carboxylic acid. Okay, but again, you know, the sort of, once we generate our electrophile, then we know what's going on here. So the key thing that we got to worry about is what the heck is this aluminum chloride doing for us?
Did you say that that was the catalyst?
It is a catalyst, yeah. And again, it's going to do the same thing as we saw in these other reactions, where it's going to turn this acyl chloride into an even better electrophile. right? So in all of these, again, benzene's kind of a crappy nucleophile. We have to be able to prep our electrophile so that it's a really good electrophile first. Not something we had to do when we were working with like a Grignard, which is a banging nucleophile. No problem attacking that carbonyl carbon. Here we got to make it an even better nucleophile, or electrophile.
I thought LDA was the banging base.
It's a banging base, yes. Now we're figuring out some banging electrophiles here.
Oh, that's right.
All right. And just note here, these are what are called the Friedel-Crafts reactions, because those are the two scientists that invented them or discovered them. Okay, so now again, what the heck is this aluminum chloride doing for us? So the first step is actually this chlorine reaches over and attacks that aluminum, right? So aluminum chloride, we actually kind of put it into a similar category as the boron containing compounds, right? Aluminum, you kind of think about it in two different ways. Sometimes as the Al3+ ion. Okay, but you can also think about it, if you were to think about it in a covalent sort of complex, it's only got 6 electrons in its octet. So just like we see with boron, when it has 6 electrons in its octet, it's relatively acceptive for electrons, right? So aluminum chloride in the same way, it only has 6 electrons in its octet, so it's going to accept this pair of electrons from chlorine. Okay, this forms this intermediate here, which then just breaks this chlorine carbonyl bond. And so we get our, again, our whole shtick here is we have to create a really good electrophile. This is our ecyllium ion. This is the electrophile that we're going to need for this reaction here. Okay. One thing I want to note about these ecyllium ions, they behave quite differently than a regular carbocation. Remember, carbocations, as we saw, actually we sort of like illustrated it in that experiment we did at the end of the semester last semester, but nonetheless, they like to bounce around, right? So keeping a carbocation localized is very difficult to do. They have a tendency to bounce to whatever the more highly substituted carbon is. Here, that's not the case with the ecyllium ion. It's actually stabilized through resonance. So since a big part of this chapter is resonance structures, everybody give me the other resonance structure that you would expect for the ecyllium ion. And again, this is how it sort of keeps that positive charge localized on in that position there instead of bouncing around to other carbons. There are no hydride shifts with an ecyllium ion.
Would it be a double bond with a negative oxygen?
No, I kind of see where you, no, it's actually, so this pair of electrons comes down here. So it's a weird looking one, don't get me wrong, but it's a triple bond with a positive charge on the oxygen. Okay, but because of this resonance stabilization, you don't have any hydride shifts with an ecyllium ion. All right, so then in this reaction, we're going to, again, that's what's going to play the role of an electrophile. Benzene's going to act as a nucleophile, attack that ecyllium carbonyl carbon. I don't know if it's carbonyl anymore. This creates our carbocation intermediate, which then we have a base that comes and removes that hydrogen, which donates that pair of electrons down, forming our aromatic ring again. Okay, and so this is, again, this is acylation. And again, I think that the hard part here is not the bottom part. That's just a generic electrophilic aromatic substitution. It's the activation of that electrophile that's different between each of these. Okay, and then just note, we saw something similar with this when we were dealing with the aluminum hydrides. But aluminum chloride will actually also, once you've acylated that compound, that benzene ring, aluminum chloride will actually bond onto that as well. It will react with that carbonyl oxygen. Okay, and you can get it off pretty easily by just adding water. The key thing here is that we have to use more than one equivalent of our aluminum chloride. That's really all this whole slide is trying to hammer home here. The fact that you actually have to have way more aluminum chloride than you would think, because not only is it going to be consumed in terms of generating your acylium ion, it's also going to be consumed in terms of reacting with the carbonyl oxygen. Okay, so when you do these reactions, you have to end up having them with more than just one equivalent of your aluminum chloride. Now, it turns out, right, so this was a great way of acylating your benzene ring. Well, what if instead of having, what if you wanted this R to just be a hydrogen? What would this compound be called? Does anybody remember?
Benzaldehyde.
Yeah, so if you wanted to form benzaldehyde, it turns out that's a little bit more of a pain in the butt. Mainly because you would have to start out with this compound here, which is quite unstable. Okay, so that's a different scheme for forming benzaldehyde than otherwise acylating a benzene ring. So it turns out that how you do this is you take carbon monoxide and hydrochloric, or rather hydrogen chloride gas under high pressure, and they will form that unstable formal chloride intermediate, right? But unfortunately, the bottom line is you can't just buy formal chloride off the shelves. It doesn't sit in a bottle in your stock room. So you have to prepare it and then immediately treat that with your aluminum chloride, apparently also copper chloride, don't know what that's doing for you, but copper 1 chloride, and your benzene ring in order to get benzaldehyde. All right, so a little bit more of a pain in the butt scheme for getting benzaldehyde as opposed to other acylation products. Okay, so that's how we acylate. Now we're going to go to our alkylation reactions, right? So this is just sticking an alkyl group on your benzene ring. Again, these are just the same sort of electrophilic aromatic substitution, right? So I'm going to be substituting a hydrogen now for some alkyl chain. Again, I'm going to be using the aluminum chloride. All right, so everybody take a second and see if you can't figure out what the aluminum chloride's doing for me. I'll give you a hint. It's very similar to what we saw previously. All right, so again, aluminum chloride. Aluminum lacks that full octet, so it can accept electrons. This gives us this type of intermediate here. And then what you should notice about this right here is that it is just going to be an incredibly good leaving group. right? Chlorine is more than willing to accept those electrons once it has a positive charge. So then what we're left with is a carbocation intermediate, right? Or that's what's going to be our electrophile that we generate for this reaction, is a carbocation. All right, and I feel like I've effectively beat it over y'all's heads, hopefully at least, but then from here on out, it's just the generic scheme where benzene acts as a nucleophile, attacks that electrophile. We get a carbocation intermediate, and then we have a base that removes that hydrogen to reform our aromatic ring. Okay, now with this one, we actually have something a little bit more difficult to consider here. So everybody take a second and give me the product that you would expect for this reaction. You don't have to worry about the actual reaction mechanism, but just give me the product. Okay, right, so the whole idea is that we're alkylating this benzene ring. So what we're gonna do is we're gonna remove this chlorine with the aluminum chloride, and that will form a positive charge there. And then our benzene comes and attacks that carbocation. All right, so that's how we get our product here, okay? But there's also a second product in this reaction. Does anybody have a guess as to what that is? What do we note about this guy right here?
It can be a hydride shift.
Yeah, right, so a primary, here we have a terminal or a primary carbocation, the least stable of all the carbocations, right? So what's going to also happen is we're going to have a hydride shift that will occur in order to generate a secondary carbocation, which is far more stable, right? So there's a reason why, like, hampered on that whole, the fact that you're, oh crap, what do they call it? The acylium ion, how that positive charge stayed localized on that carbon because of resonance, right? You didn't have to worry about any hydride shift. In the case of alkylating, in the case of forming your carbocations, when there is no sort of resonance stabilization, now you do have hydride shifts that will occur, right? So you have, in this case, a second product, and that is actually going to be the major product in this reaction here, right? Because the secondary carbocation is that much more stable. If you were able to form a tertiary carbocation, this number would be even bigger than 60 to 80. You could have even 100% formation of that tertiary carbocation product. Right, so now digging back in our brains, remember, primary is the least stable carbocation, followed by secondary, followed by tertiary. Tertiary is the most stable. And the reason that this is such a big gap here is, as we saw, temperature and time play an important factor in how much hydride shift is actually observed. I know that you guys poured over that data from the experiment at the end of the last semester and saw that that was the case. Okay. And we're going to see why this is in a second, but these reactions actually, you have to carry out these reactions with a huge excess of benzene. Okay, the reason for that is that an alkylated benzene ring is actually more reactive than a naked benzene ring. So if you don't have a huge excess, what you end up doing is just having multiple substitutions on the same ring. So if you just want a single alkylated product, you have to have an excess of benzene. All right, again, if we didn't have an excess, then what would we would be looking at is like something that has multiple chains coming off of it. Right? We don't want that, or I mean, if you did, then great, you wouldn't have to worry about it. But if you didn't want that and you just wanted the single alkylated product, that's why you'd have to have an excess of benzene in there. The other way that we can get around this, if we don't, well, let's say we just don't have that much benzene to work with here, is by first acylating it. Okay, so that's first taking your benzene ring, reacting it with an acyl chloride in the presence of aluminum chloride, and creating your acyl substituted benzene. And then following that up with a reducing agent that's going to reduce that ketone group. All right. The reason why this works is because acylated benzenes are less reactive. So here you don't have to worry about having an excess of benzene. And we'll get much further into this, what benzenes are more reactive and less reactive next lecture. But nonetheless, that's why these two slides exist. You know, you get into the same endpoint here, it's just different conditions, right? So this is first acylating and then following this up with an acyl substitution. Let me just note here, what would happen if we had just an alkene in the presence of H2 and our palladium catalyst? What would we get?
An alkane.
An alkane, right? Notice that our benzene ring is not reduced by our palladium catalyst. Again, that has to do just with has everything to do with the fact that benzene is just that much more stable than a regular alkene because of that aromaticity. Right, so notice here, hydrogen gas in our palladium catalyst, it does successfully reduce the carbonyl group. It does not reduce the benzene ring itself. We'll see in a second how we can reduce the benzene ring if that's what we want, but yeah. The other thing to note about this hydrogen gas and palladium catalyst is it only works if your carbonyl group is next to the benzene ring. Okay, if that carbonyl group is further away than just one removed, it's not going to reduce it. That is why we have this other example down here, this Wolff-Kishner reduction. This is a similar way where you're going to form your acylated benzene, and then you can do a further reduction. This one will work on all carbonyl groups. All right, so this is going to play into this like chemioselective idea. So let's just do a, what the heck do I mean by that sort of thing? Somebody's jamming outside. All right, so everybody take a second and give me the products of these two reactions here. All right, so again, the key here is that our palladium catalyst is going to only be able to reduce the carbonyl group that's directly next to the benzene ring, whereas Wolf, whatever his name is, will be able to reduce that carbonyl group no matter where it is. And I guess let's be careful, like when we say reduction, we're talking about like full reduction, basically chopping it off, right? Not to the alcohol group sort of thing, which is sort of what we're used to. So I guess I'll be more careful with my language there. All right, last thing we're gonna finish off with is with two other methods of acylating a benzene ring that we actually are, I'm sorry, not acylating, alkylating a benzene ring that we already know about here. So first of all, what the heck type of reaction is this guy here? I have a chlorobenzene with, what the heck is this? Anybody remember this dude's name? Failed car manufacturer?
Suzuki.
Yeah. So we already learned about this back in our organometallics lecture. This is the Suzuki reaction. We have this organoboron, and we're going to react it with an acylated alkyl halide. No, I'm sorry. That's all wrong. With a halogenated benzene. So notice that at the very beginning, we learned how to form this. Right? We learned how to form one of our chlorobenzenes. So now we could turn around and use this in a multi-step synthesis along with a Suzuki in order to alkylate that way. Notice that here, I don't have to worry about any sort of carbocation rearrangements. And we also saw the same thing with our organocuprates, right? So this would be Gilman. Again, we have a halogenated benzene or bromobenzene reacting with an organocuprate to form an alkylated benzene ring.
Will Gelman's not react with benzene because they're both essentially nucleophiles?
Yeah, right. So Gilman will only react with alkyl halides. You know, it's got to have that halogen group on there. And yes, absolutely, because the Gilman reagent is the one that's playing the role of the nucleophile. Okay, so that about does it here. We will pick up on the next slide where we left off here. Do you guys have any questions so far? So hopefully, you know, the other thing that I think was especially difficult about this last section was the fact that we had this 2-week gap between when we finished lecturing to when we actually took the exam, which in theory, everybody's like, yay, more time. But let's be real. You got to have it directly after for it to actually be like fresh in your mind and all that good stuff, right? So I know that everybody was pumped that exam 2 got pushed back, but it probably wasn't necessarily the best thing for us all. Again, just trust me when I say that I have y'all's best interest. If the grades don't look good or something, I'll come up with something, a retake, something like that. You know, the goal doesn't change. I hope that nobody heard, all I got to do is show up and I'll get an A. It's not like that's the case. But if y'all just keep up on doing what y'all are doing, y'all are a really good group. Trust me when I say I got your back on this whole thing. I know that this is a weird time. Okay. Any questions? So again, just take note, those labs are posted, the labs posted. Really all you got to do for this particular experiment is to get your notebook kept up. And then this, as well as the one that we do once we get back from spring break, will be what you'll do your second formal lab report on. Cool?
Is spring break next week? Like
Spring break is next week, yes. So that's actually why the due date for your lab notebook isn't next Friday, it's the following Friday, because I'm not going to have anything due over spring break. Yep. So everybody take your spring break, enjoy. I know we're all confined at home. Make sure like to go for a walk around your neighborhood. Hopefully you guys are getting outside at least a little bit. Everybody and their mom is trying to go to Woodward Park. I wouldn't do that. Keep yourself distanced, but definitely make sure to take a walk around outside. It's it's not good for your mental health to just literally be stuck inside all day, every day, right? So yeah, I hope you guys are at least sort of like taking a walk around. I hadn't realized how much of my neighborhood I haven't explored yet. So yeah, it's been nice. I swear this whole thing was secretly organized by my dog, who is the biggest benefactor of this whole thing. But yeah.
Yeah, dogs have been the real winners.
They really, yeah, the dude is spoiled. Yesterday he went for a long walk, napped up until the time when I woke him up to take him on a second walk. So he's just beyond spoiled at this point. All right. You know, feel free to email me over the weekend if you guys have any questions or anything like that. But yeah, we'll just pick up where we left off on Tuesday.
Are you posting any of the homework for this new chapter over the break, or?
Yeah, I'll work on that right now.
I mean, you don't have
The
to,
video
but
will
you know,
be
like whatever.
posted. No, yeah, we got to do the homework, unfortunately. I'll post this video. My goal is actually, I got to see if I can download it from the Zoom server and move it over to YouTube, because they're starting to crack down on like, whatever, having closed captions and all that good stuff. So, but nonetheless, the video for this will be posted as well.
Are you gonna update the version, updated version on where?
So sorry, you cut out like halfway through that question.
Are you
The
going to
syllabus.
update the?
You cut out on
He
update.
wants to know if you're gonna update the syllabus.
The syllabus. Oh, no. So I'm actually not allowed to update the syllabus. The syllabus is one of those things that once they get touched, we're not allowed to touch them again. If there's, what in particular would you, are you curious about having changed or not changed?
Well, because we pushed the test back, so we're kind of behind.
Right.
So are we just going to follow the same way?
So what's going to happen is exam 4 is likely going to get scrapped, and just your final exam will be more heavily weighted for exam 4 questions. So again, one of the things that I'm going to have the power to do now is to be able to pick questions. So yeah, so what my way to make that up in terms of the schedule. So I did post a new schedule on Canvas. And if that schedule sticks, what we've done is we've cut a chapter out, and we're going to nix exam 4. And again, my plan is to just make it so that the final is slightly more exam 4 questions than everything else. Cool. So yeah, so I can do stuff like that. I can post schedules, but I'm not like, there's just weird rules about touching your syllabus. It actually gets submitted to like the administration, so you're not allowed to change things afterwards. Cool. All right. If you guys don't have any questions, we're done here. Enjoy your weekend. Again, stay sane, stay safe.
Later, y'all.
Cool. Are carbocation intermediates as famous as tetrahedral intermediates?
Almost as famous. They're a little bit more unpredictable. So.
All right, cool.
All right.
Bye.
Bye, guys.
You done? Nice. We're gonna go.